Printed circuit board hatched ground plane electrical resistance. In some cases you can meet the option to have solid or hatched ground plane in your printed circuit board. We will not discuss pros or cons of this option, only the pragmatic question matters. What is the resistance of the hatched ground plane and how to simulate the hatched ground plane? Here is the sample of the hatched ground plane. You see the periodic structure composed of hexagons. The real board dimensions are 18 by 10 centimeters. Hexagons are very small. The side length is only 0.3 millimeters. So the hexagons look like teeny holes in the plane. I will simulate only a small piece of the board to calculate the equivalent resistivity of the board. Is made of copper and the foil thickness is 0.035 millimeters. Let's start QuickField now. In QuickField I create new problem. Problem name board. Next. Problem type is DC conduction, as I would like to simulate electric current distribution in the board. Model class is plane parallel, length units are millimeters, and the board thickness is 0.035 millimeters. Finish. On the left you can see the problem pane, and on the right you can see the geometry model editor window. Here you can draw the geometry model using QuickField built-in tools, or you can import the geometry model from the DXF file. DXF file is used by many CAD systems to interchange plain geometric models. I already have the model prepared, so I will import it. Here we see a piece of the hatched ground plane. To distinguish one geometric object from another, we should assign labels. Through labels we also assign physical properties. Switch to the select mode and click to select the block. Or I better zoom in. Now switch off the zoom in, click. Now let's see all the model. This is copper, and I can open properties dialog and type in the label here, copper. The label appears in the tree. If I double click the label, I can specify physical properties. For the copper I specify electrical conductivity, which is 56 megasiemens per meter. Okay. Other blocks are non-conducting holes, so I do not assign any label to the holes. So that's all for materials. Next, let's deal with boundary conditions. Let's say that the bottom side is grounded. I select these edges, open the properties and type in the label grounded. For this label I specify 0 voltage. And let's the top side has positive potential. I select top side edges, open the properties and type in the label V+. For this label I specify positive electric potential 1 millivolt. That's all for the geometric model and for the labels. The last step is to build the finite element mesh. Just click the button and the mesh is built. Now I will save all simulation files and run the analysis. The result is ready. Let's take a look. Here you can see the current density color map. Let's measure the total current. I will adjust the field picture and switch on the current density vectors so you can see better the current paths. Small. Okay. I will use the contour tool to calculate total current passing from the top side. Just build the contour in any place, crossing the current paths. Follow to the integrals, and here is the current. 0.34 amperes. In fact, you can draw the contour in any place, just to make sure that you cross all the current paths. This contour should give the same current value, 0.34 amperes. Now, if I divide the voltage drop by the current value, I will get the resistance. 1 millivolt divided by 0.33 amperes, the resistance is 3 milliohms. I will add the solid copper in the model and compare the current values. So I open the geometry model, copy, paste. This is the solid copper sheet, so open properties and assign the label copper to all objects. Edge labels are the same, ground at the bottom, positive voltage at the top side. Build the finite element mesh, save all simulation files, and run the analysis. Now that's all. Here we have solid and hatched planes side by side. I will adjust the field picture and switch on the color map of electric potential. Now you see the potential distribution is identical. Let's compare the currents. Again, I will use the contour tool, integral hatched plane current 0.34, contour clear, and the solid plane current is 1.96 amperes. 0.96 divided by 0.34. Hatched plane conductivity is 5.76 times lower comparing with the solid plane, and equal to 9.7 megasiemens per meter. Now we can draw hatched plane as a solid plane and specify equivalent electric conductivity of the plane as 9.7 megasiemens per meter. On our website, if you search for the PCB hatched ground plane electrical resistance, you will find the example page. Here you can read about problem setup, browse the solution section, take a look at the results, and download the simulation files. Simulation files may be viewed using any QuickField edition, including free QuickField Student Edition.